Hello everyone. We are now going to look at a set of topics that are related broadly to the area that I am going to refer to as debug and test. As we'll see, there are a slightly more nuanced way of looking at these issues. They are a very important part of how you actually go about creating reliable and robust programs, and also just to sort of ensure correctness of the programs. So this is something that we are going to be looking at. We are going to look at a few examples, but primarily from the point of view of many concepts that you need to understand in terms of how these things get implemented, especially in the context of embedded systems. So debugging is an essential part of pretty much any software development. In an ideal world, there would be no reason to do any debugging, right? Because the first time you write a program, everything just works perfectly. Of course, we don't live in an ideal world. What happens is that the programs that we write have various kinds of issues, some kind of bugs, some problems. The reasons for those are many. Some of them we have already discussed in the past, but there are also fundamental reasons why there are good reasons to believe that it may not really be reasonable to expect that you can write entirely bug-free complex programs at first shot in a systematic manner, right? In other words, bugs are a fact of life. It's very unlikely that we'll be able to get rid of them entirely. There are certain approaches to programming, such as formally specified programming approaches and so on, that try to minimize the occurrence of bugs. But at the end of the day, it is a very complex system that we are building up, and therefore we need to be able to deal with bugs as and when we encounter them. So one of the slightly more sophisticated ways of debugging, of course the most primitive form of debugging that we can think of, is pretty much just insert print statements throughout your code, right? And as and when you reach a certain point in the code, you get some kind of an indicator, a printed statement, something on the screen that tells you that you have reached a certain point in the code. And if you don't even have access to printf, right, you don't have a console, the even simpler version of that is to sort of make use of an LED to sort of indicate some kind of a sign of life that you have reached a certain point in your code. Now, obviously this is very crude. The amount of information you can transmit through LEDs is minimal. Even through printf statements is not very great, for the simple reason that adding too many printf statements will dramatically increase the size of your code. More importantly, it can also give rise to certain kinds of bugs that occur only in the absence of the printf statements. How does that happen? As we have discussed earlier, printf statements tend to be slow. They change the timing with which certain operations are performed, and therefore having a exact reproduction of the runtime scenario under the conditions of a printf statement may not always be possible. Now, more importantly, right, when you are dealing with really large programs with multiple functions that need to be called one from another, knowing where to insert a printf statement in the first place may not be straightforward, right? So rather than trying to go around just sprinkling printfs all over your code and then finding later that removing them or converting them into debug only statements becomes hard to do, there is a better approach, and that's where essentially the power of so-called single step debugging comes in, right? The basic idea behind single step debugging is that you can define something called a breakpoint in your code, right? And this is essentially a point in the code which normally we as human beings would basically take the source code that has been written, the C code, and say the moment the program gets to this particular point in the code, halt and wait for the user to tell it to continue. Now, hopefully some of you already noticed that there's a problem here, because the C code that we write is not exactly what is finally running on the processor, right? The C code gets converted, compiled into some kind of intermediate representation, and finally into machine language. So what is actually running on your processor is a set of machine language codes. So it is possible that a particular line in the code, in the C code that you wrote, does not even exist or does not correspond to any final machine code in the actual system that is operational. But in most cases, it does correspond to code that exists in the final machine language. And more importantly, when you compile your program under debugging conditions, you can more or less ensure that the code is retained, right? What that means is that it's actually possible to take a point in your C code, mark it in whatever tool you are using for your debugging, and the compiler will then generate a suitable version of the executable binary, which actually has a breakpoint associated with it. Right? Well, it's not exactly the compiler that's doing this. The compiler, of course, puts in some kind of assistance, but the actual work of putting in the breakpoint is done by means of usually what are called interactive debuggers. So what that means is that the debugger, which is itself a program, right, which most likely is going to run on your host computer. What do I mean by a host computer? As we discussed earlier, most embedded systems are cross-compiled, meaning that you are probably working on a PC, it could be a Windows PC, it could be a Linux PC, writing code and compiling it, but the compiled code, the output that you generate is not going to run on the Windows or Linux PC that you have, it's going to run on your microcontroller. Now, that cross-compilation process, of course, generates the executable code, but the interactive debugger also runs on the host, which means that it needs to have some way of communicating finally with the system on which your code is actually going to run. Now, one of the things that's done is, in order to implement the equivalent of what's called a breakpoint, is that you can actually go in and modify your code and insert an invalid instruction somewhere in the code, right? You literally go and modify the binary instructions corresponding to your code and just make it an invalid instruction. And this is where we use the power of how modern processors are built. When a processor encounters an invalid instruction, it doesn't just sort of crash and burn or go into an infinite loop. It actually generates an exception, an invalid instruction exception. What that means is, anytime we encounter an invalid instruction, we can sort of take it to imply that yes, we have hit a breakpoint in the code, and we can go check what was the program counter at which it halted, and sure enough, if that corresponds to a point at which we have a breakpoint, then we can go back to the user, give them control and say, okay, now we hit the point that you had marked, how do you want to proceed from here? Okay. So of course there can be scenarios where inserting an invalid instruction just causes a crash of the system. Crash meaning that the program stops working. If there is an operating system, it usually returns control to the operating system. It also results in something called a core dump, and a core dump essentially is something which basically is a binary image of the memory of the system, which can be used in order to help with debugging, because a person who knows exactly how the memory is laid out in a system will be able to look at the core dump and say, okay, this is how the memory of the system looked, and this is how I can use that information in order to actually find out what the state of the system was when it crashed. Now, that's not really what we want in terms of debugging. What we want is interactive debugging. So we basically create a software invoked interrupt, but a software invoked interrupt is usually called an exception, right? So you can basically have some kind of an exception, and you handle that exception by saying, okay, now I know that this happened because of a breakpoint that was set by the debugger. Return control to the debugger and ask the user what to do next. Okay. So this is a very powerful construct. It basically allows you to sort of snap right into the middle of a piece of running code and halt it at any point that you want, right? And what makes it even more powerful is you can have so-called conditional breakpoints. And a conditional breakpoint is one which basically says, okay, it's not just that I'm immediately going to return control to the user. When I hit the breakpoint and the exception gets called, I'll first check if some condition was satisfied. Perhaps I'm interested in whether I have a for loop, and has the for loop, the counter in the for loop, has it finished the first 100 iterations, right? On which iteration am I? Maybe I put a breakpoint saying if I greater than 100, then break, right? And that's easy enough to do, because in any case your conditional execution is being handled by a piece of software, the exception handler. Now another variant of that is that you could also define something called a log point, and a log point is a variant of a breakpoint. Basically what it says is, rather than returning control to the user and making it interactive, all that it says is, when this particular point in the code is hit, you just log the values of whatever variables you have of interest. right? It could be the present state of the system, so that later on somebody can just monitor the logs and sort of say, okay, is the system working properly or not, without necessarily having to actually interactively step through it, which can be a slow process. So this whole idea of stepping for debugging, right, essentially means that after the breakpoint, you can allow single cycle steps through the code, and an illustration of that is shown over here. Basically, you have a CPU which has its own internal registers, and the way that this works is you basically have a clock associated with the system, right. The normal behavior of the clock is that it's a square wave in the form of electrical signal, which basically goes between, let's say, some 0 volts, which is ground, and some VDD, which is a high voltage. So the clock is just an electrical signal that toggles between two values. What we are saying is when we hit the breakpoint, right, which could happen because of an instruction or something else, it could even lead to a different mode of operation where essentially the clock that is being supplied to the CPU is just halted, right. Now this becomes particularly useful when we are actually using some kind of hardware assisted debug, and what I mean by hardware assisted debug will become clear in a few more slides, right. In pure software assisted debug, it's not really possible to stop the clock, because if you do stop the clock, then your CPU has just stopped, you have lost all control over it, right. So you never actually stop the clock in pure software debug. What you do is you have some other way by which you can control how individual steps of the clock will, individual instructions will be executed from that point on, right. But in hardware, you could actually get to the point where you actually break the clock, you stop it from toggling, and then you can control the clock from an external mechanism and say, okay, I will just single step it, I will allow it to go through one up down variation, right, which is one cycle, and I can space those cycles at whatever point I want, and in the meantime I can basically examine the contents of all the registers or anything else inside the CPU or the memory, provided that I have the right kind of controls put in place, right. And as this says, this can only be done with hardware support for the debugging, right. This is usually referred to as some form of in-circuit debugging. There is, especially in the context of embedded systems, each individual vendor of the embedded system will have their own variation of how you can do in-circuit debugging. ARM, for example, has many different sort of custom architectures that they support, which allow for certain kinds of in-circuit debugging. And on top of that, a particular company like, let's say, ST Microelectronics would provide their own interfaces to that along with their own software. Unfortunately, what this means is that in the majority of the cases, this ends up being fairly customized, right. Each and every different CPU, and in fact different vendor of a given class of CPUs, you will find that they have their own ways of handling this, right. And if such a scenario happens, then the only way to handle it is basically go read up about how the debugging system for that particular vendor works and then make use of it. Now, why do we need this kind of hardware debug in the first place, right? The first thing that we need to be very clear about is hardware and software are not exactly the same. Now that might look like an obvious statement, but what I mean over here is something a bit more subtle. It is that you could also have chosen to take your entire system and simulate it in software, right, and that can usually be done. Pretty much any, in fact, WalkV, the website that we have been using for a number of demonstrations in this course, is basically running software simulators of various kinds of processors, right. The problem is the software in general cannot model all physical conditions. Even within WalkV, you will find that for certain processors, certain kinds of behaviors are not completely modeled. More importantly, even where they are modeled, certain kinds of uncertainties, including things like what is the rate at which DRAM needs to be refreshed, or what is the latency associated with accessing data from an external memory, or what happens when there is a race condition between two push buttons being pressed, are extremely hard to even model, right, let alone to get it sufficiently accurate that it can model all possible physical conditions. Real-time interaction in particular becomes extremely hard to simulate. So are analog inputs, right. Analog inputs to some extent can be modeled by just having an analog signal that is connected to your the pin of the emulated CPU or the simulated CPU. But especially the moment you have some kind of non-deterministic or noisy behavior, that becomes harder to model in a way which is, well, deterministic, right? And by deterministic, what we mean is something that is repeatable, something that you have exact control over. So each single step will be different, and not only that, it will end up being different than what actually happens in the real world scenario. And at the end of the day, because of all of these conditions, the moment you have some kind of a multiprocessor system or a multitasking system, that makes it even harder to debug. So the bottom line is that simulators can only take you so far. Of course, if you have a simulator, then a lot of the things that we talked about, single step debugging and so on, are relatively very easy to implement, right? The simulator can pretty much just stop the program at any point and show you the exact state of every single register inside the CPU. Hardware though behaves differently, right, and is a lot harder to get the exact state of. Now, having said that, there are mechanisms by which you can tap into the hardware and actually get some useful information out of it. One of the standards, the electrical circuit standard for this, is what's called JTAG, right, which basically JTAG stands for Joint Test Action Group, and from the name you can probably infer that this was defined originally for testing hardware. That's why the name test, right? It's an IEEE standard. IEEE is the Institute of Electrical and Electronics Engineers, and they are responsible for standardizing many of the electrical and communication protocols that are used. Standards are important because without standards, whatever you define for your system is unlikely to work on another system, and it basically makes it very hard to sort of build interoperable mechanisms. So JTAG was specifically devoted to the problem of testing circuits, and the approach that they took was, if you have, let's say, multiple digital circuits that are present in an overall system, you want to know the state of every single register or flip-flop inside each of these devices, right? The only realistic, or rather the only normal way that we would think of would be that I need to actually take wires out for each and every one of those registers, but that's impractical because of the number of registers that are going to be there inside each individual device, right? You are probably going to have like thousands of bits on average, right? It could be in the millions, and you simply don't have that many pins that you can take out of each device. And even if you somehow manage to get, let's say, 1000 pins out, you don't have a easy way of sort of coordinating, okay, 1000 from here, 1000 from here, 1000 from here, how do I collate all of them and get something useful out of that? So instead, the approach that they took was, they said, like, let's go to the other extreme. We just have one set of pins, right? We'll basically have a clock, and we'll also have one pin which is called the input and another pin that's called the output. And out of this, we'll construct what's called a daisy chain. And a daisy chain basically looks like this. The input of the overall debugging system, right, the TDI pin, the test debug input, goes into the first device. It actually goes through each and every register that is present inside this device in a chain, and then finally makes its way out through TDO. Okay. Now obviously it's not just a short circuit, it's not just a wire that goes through over there, it actually is connected to each and every one of those registers or flip-flops in a way that that register or flip-flop can actually use the information that is being pushed in through TDI, but eventually it makes its way out through TDO. What happens when it goes through TDO is, it then can be fed into the TDI of the second device. It then goes through each and every register over here, comes out through TDO, comes in through TDI of the third device, comes out through TDO, and finally it comes out all the way back to the host. Right, so what do we do with this? We have some mechanism by which I can basically send a wire, or rather send an electrical signal through a whole lot of registers, chain them through multiple such devices, and finally pull them out at the other end. Okay. Now there are a couple of interesting things that we can do. One is, we have this TMS signal, which, although it's shown as just shorted together for all of these, it can actually be used in order to activate in some way the debug state of each and every one of these devices. By sending a suitable combination of signals, I can basically say which of these devices is meant to be debugged. All the others will basically go into a pass-through mode, meaning that their TDI will just get connected to TDO. This one will have it connected through all its registers, and this one will just perhaps be a short circuit. Okay. So obviously what that means is I have some logic inside my each of these systems over here, which either allows me to connect the signal through the registers or allows me to bypass from input to output. Okay. Now what if I have not bypassed it, that is I actually have the signal going through all of the registers? That's where the T clock comes in. What it says is that for each pulse of T clock, that is T clock going 0 to 1 and then back, and then 0 to 1 and back, 0 to 1 and back, 0 to 1 and back, each of these is called a pulse. For each of these pulses, I can push in one bit on TDI, either a 1 or a 0. And that bit will basically go through each and every one of these registers in a chain. It will first go into the first register, then that bit will go into the second register, while another bit goes into the first register. Then the bit goes into the third register, the second bit goes into the second register, the third bit goes into the first register, and so on. It's basically, it becomes a long shift register. Okay. Now, what do we do with that? What that means is that over time, if I take, let's say, 1000 clock cycles, I can actually send in the bits corresponding to each and every one of the registers that is present inside. I can set them to a known state. And once I have done that, I can essentially switch the mode of this and basically say, okay, I have set all my internal registers to a known state. Now let me actually pulse the actual operating clock of the overall system, right? Give it one clock tick and see what happens. There is some state corresponding to the internal registers. There is some combinational logic. Under those conditions, how does this behave? What will be the next state of each and every one of these registers? So you pulse the clock, capture all of those internally, and then you do the same thing. By again just pulsing T clock, I can now read out every one of those bits on TDO and get it all the way back to my host and say, okay, this is what I sent in, this is what happened when I sort of pulsed the clock, this is what I got out as a result. Thousands of clock cycles for effectively getting the output corresponding to a single clock on this particular system, right? But it turns out that that's actually still quite useful because it gives you such a detailed level of control over the internal state of the system that you are actually single stepping a piece of hardware directly, which means that even though it is slow and there is extra logic involved in the register construction and so on, it turns out to be a very powerful mechanism for actually testing digital circuits. Okay. This approach is usually called the boundary scan. What that means is you only have access to the boundaries of the chip, basically the input and output over here, and you are somehow able to scan through the entire thing and get an update on the state of the system. Okay. Now, how is all of this relevant for us? It turns out that because all of these registers are connected in a chain and you can set the values of individual registers or read the values from individual registers, you can now make use of it in the context of software by basically saying I will provide access to certain kinds of debug modules that are present inside the chip, right? And I can, for example, use this in order to read out the register values. What is the state of the program counter? What is the state of register R0, R1, R2, whatever are the registers present inside the system? What are the control and status registers like? What are the flags? Every single one of those could be taken out in the JTAG chain. And in addition to that, because of the fact that you can set individual registers, you can even use this in order to toggle certain bits and eventually slowly write values into memory. Okay. Yes, of course it is slow, but on the other hand it gives you an unbelievable level of control over what is actually happening in the hardware. So it becomes a very useful debugging tool. Right? It was designed primarily for debugging hardware. It has been sort of repurposed for software debugging, but it has turned out to be very effective in that context, right? So in the context of software debugging, you may not actually have all of these chains being put to the uses that they are normally used. What you would have is that you would directly talk to one module somewhere inside the CPU, whose job is to basically do at a slightly higher level things like single stepping or controlling the program counter or things of that sort. right? The moment you have some way of getting data into and out of a system in a controlled manner, it means that you can basically program it to do whatever you want, and that is what JTAG enables. Now, JTAG is complicated, it is highly capable, it is also slow, and it does much more than what you really need for software debug, right? As a result, people came up with other standards. The one that is most popular is what's called Singlewire debug and is used primarily with ARM microcontrollers. It basically uses, well, two wires, right? Even though it's called single wire, it uses a clock and it uses a debug data in out. And of course, if you think about it from an electrical point of view, I'm sure there's a ground wire somewhere else. So calling it single wire is really sort of stretching the definition of what a single wire is at this point. But logically, all you need is a single wire in order to get the data in, which is why it's, we can sort of have some poetic license over here and call it single wire debug. Now, optionally, it also allows you to have another wire which is called the debug output, but for our primary purposes, it's basically the debug data in and out. And functionally, it does something very similar to what JTAG would allow you to do. Rather than using boundary scan, it allows you to have direct control into the debug modules that are built into ARM processors, right? Because of that, and because it sort of gives up on some of the abilities that JTAG enables, it turns out to be faster than JTAG. It also uses fewer pins. Now, JTAG itself uses very few pins, as you know, right? It's basically sort of just the TDI, TDO, T-clock, TMS, and VCC ground effectively, right? This uses even less than that, but that by itself is not the primary purpose. It's more that it's designed for software debug, which basically makes it significantly faster than JTAG in a lot of practical contexts. JTAG is more flexible and supports more devices. SWD, single wire debug, is more specific to ARM but is faster, and if you are working with ARM processors, it is very likely that it will be a more efficient way of handling things. Now, all of this basically translates also into actual physical connectors, right? And these are things that you would very likely come across when you actually start working with the hardware. You would probably see some kind of a header like this. This is usually called a set of jumper pins, right? And you have a cable of this sort, and if you look carefully at the cable, you will also find that there are actually settings in the cable to make it such that there is only one way in which this cable can be inserted into this key, right? And as you can see over here, there would usually be some kind of a missing element with a corresponding section over here that has been basically made solid, right? So the only place that it can go is actually into this place. All of this is just, it's nothing specific to software. These are more sort of practical engineering observations that basically allow you to say, okay, the chance of going wrong in the way that you connect up such a cable like this is reduced if you do this properly. Needless to say, JTAG is an electrical protocol, which means that when you actually design and build a chip with a JTAG connector, you need to also take into account the terminations of the signals and so on, right? And the best way of going about this is usually to sort of go with known architectures or known layouts of circuits and then modify them for your requirements. That's well beyond the scope of what we are looking at in this course, but is something to be aware of as you sort of look more at embedded systems. And on top of all that, of course, we also have the software support required for the debugging. This usually comes from the point of view of various integrated development environments. What we have looked at so far has been WalkV, which is a web-based environment which is primarily meant for simulation. Some of you may have seen the WalkV VS Code extension that allows you to actually write code in Visual Studio Code, which is a local editor that you can run on your PC, and run the ARM compilers and generate code and even run a simulation locally, right? Those of you who have actually worked with board, right, already would have come across a development environment either like STM Cube, or you might have come across software like Keel or Code Composer Studio from Texas Instruments and so on. The Eclipse platform is a sort of general purpose platform that has been adapted by many of these people in order to build up an overall development environment. Now the point is that this is primarily from the point of view of convenience and also consistency. People get used to a certain way of developing code. The whole idea of how do I set breakpoints, how do I watch the values of variables, how do I sort of incrementally step through the different parts of the code and so on. The more familiar it is, the easier it is to use. Most of these development environments also integrate quite well with hardware debuggers and can be used for the actual debugging process itself. So to summarize, the debugging is an essential part of checking the program correctness, right? As I said, there are certain tools like formally verified processes, formal specification processes and so on that are actually even more important in some sense than debugging, because to some extent they allow you to avoid certain classes of bugs by construction, right? By the very way that the program is designed, you can pretty much guarantee that certain types of bugs cannot exist. If the program compiles, it guarantees that certain kinds of bugs cannot exist. However, this is beyond the scope of this course, but is definitely an important area to keep track of, especially in the context of embedded systems, although it is applicable in general for any kind of software, right? And future developments are likely to make these more useful, more important as we move forward. There are of course two variations on how you could do debugging. One of them is pure software based debugging. In the C programming course, we looked at how to use GDB to some extent, right, for basic debugging in software. That requires some level of support from the operating system. It may require modifications to the actual executable binary so that some debugging symbols and so on are added, right, the compilation process is modified, but is usually minimally invasive. Hardware support, however, is not as straightforward. You require specific hardware support, but especially in the context of embedded systems, it may be the only way forward. It may be the only practical way that you can actually get something debugged.